How's the frequency? I changed frequency. We okay now? Yeah. Okay, sorry. So the company that grows this aluminum oxide or builds the equipment for this is up here in New Hampshire, and it's about a quarter the size. The equipment's about a quarter the size of this room, and it has to get the melting temperature of aluminum oxide is about 2,000 centigrade, so it gets pretty hot. And they make the equipment, like I say, it's a quarter size of this room, about as tall as this room. They make what they call a boule, B-O-U-L-E, of sapphire or aluminum oxide that's about this big. And that boule, like a great big football or rugby ball, I guess is more accurate, doesn't have points on the ends, is worth about $100,000, okay? But it takes about a month to 6 weeks in the furnace. And it's a $1 or $2 million furnace. And this company in New Hampshire sells this. Who do they sell it to? They sell it to the Chinese. And I said, well, who needs all this single crystal aluminum oxide? It turns out every LED has got a substrate of aluminum oxide. So this stuff is going to be cut up into little squares or rectangles, and then they're going to put the gallium arsenide laser or whatever on top of that to make the LED. Probably because of coefficient of thermal expansion matching, okay, and whatnot. But anyway, so that's some sapphire. Now that chunk is, as it is probably worth, you know, a few dollars. And then we had to get a diamond tool to cut off the sharp edges because they just put it in a great big press, and aluminum oxide it's got better fracture toughness than most ceramics, but it's still pretty lousy fracture toughness. They just smash it to break it into little chunks because it's so hard to cut. The only thing harder in the natural scale of things than aluminum oxide is diamond. I mean, we use aluminum oxide, which we call corundum, as diamond grit, as grinding grit. You go to a hardware store and say, oh, aluminum oxide or corundum. Well, it's basically the aluminum oxide, but not in big grains like that. So they like to have big grains. But this company before that had sold about, I don't know, several thousand furnaces similar that didn't go to quite as high a temperature, a little bit different design, but to grow silicon for solar cells. And they sold these thousands of furnaces to the Chinese. The Chinese government decided about, I don't know, 8 or 10 years ago, they were going to take over the solar cell market for the world. And they were going to invest as a nation, basically. Now, they're not supposed to do this, technically. This is one of these externalities I talked about in the first day. They're not supposed to, as a nation, go out to compete against the rest of the world. It's supposed to be individual companies. But in China, it's sort of fuzzy about, is the company owned by the government or not, okay? But in fact, the government had a stated national policy that they were going to have a certain amount of solar cell production for nice environmental things. And they didn't have the technology, so they bought it from this New Hampshire company. And they basically did the same thing, just put silicon in a furnace, heat it up. It only takes about 1,600 degrees centigrade rather than 2,000, which is a lot easier. Heat it up and let it cool down, and you get these large, well, they're boules, except these are actually grown in graphite. They don't end up as a football shape. It actually has some flat surfaces. But great big crystals of silicon. Now, when people started making solar cells 40 years ago with silicon, they were taking single crystal silicon, which you had to saw cut with diamonds and make flat sheets. In fact, you know, when Intel makes a single crystal silicon, they buy that from the Taiwanese, because the Taiwanese basically went into a company called Taiwan Semiconductor Manufacturing, went into the silicon foundry business, and they just grow great big single crystals of silicon, and they kind of beat out everybody else in the world. And so Bell Labs and Intel and all these other people just said, oh, well, we'll just buy our silicon wafers from Taiwan. But those are single crystals. You don't need single crystals for solar cells. And I'm going to pass this around. You're welcome to pick them up. Be careful, they're very sharp. Okay, this is like a razor blade, but you can pick it up. This was actually grown by a company out here west of Boston. It was started by Professor Sachs in mechanical engineering, and they use edge-defined film growth where they have a little carbon fiber on either side, and they draw these fibers out of the molten bath in a temperature gradient and just grow sheets of this stuff. Now, they're sort of fragile, okay? In fact, they're ultra fragile. If I try to pull this one out, it fits in here pretty tight. I'll pass it around, but I'll probably break it, okay?
What is this one again?
That one's just a chunk of silicon. Grown very slowly, cooled very slowly. Takes about a month to heat it. It only takes a few days to heat the great big thing up and melt it, and then you cool it down, you know, at a degree per hour or something to solidify it and get great big grains, because it's very pure. Actually, it's not very pure. It's got some boron or phosphorus in there. But in any case, this thing's sort of wedged in here. I'm not sure I can get it out, but you can see the full, this is the full width sheet, and here's a piece on top. So there's the silicon solar cell market, and people were predicting, because we were getting these cheaper ways to grow silicon, whether it's that way with the big chunk, and this came from the same place of the big chunk came out of one of these. I mean, the silicon things come out of, they're huge. This is a piece that's been diamond saw cut. You'll see the chips on the edges, and that's just from passing it around, okay? It's pretty brittle stuff. It's not exactly a structural material from its brittleness point of view, but it is a functional material for solar cells. Lots of wasted energy or wasted material in just the width of the saw cut to the diamond saws to cut this stuff, and I've got a little thing to talk about that a little bit later. In any case, it's sort of interesting. This company up in New Hampshire has sold hundreds, if not thousands, of these furnaces to the Chinese, who are building a $30 billion investment to try to create a $1 trillion market in solar cells. In the meantime, you hit the, remember during the election they were hitting up Obama for the Department of Energy. He had loaned $300 or $400 million to Solectron in California, Southern California, which was supposed to be doing solar cells in the United States, and they tanked. And so the federal government they defaulted on the federal guaranteed loans for $400 or $500 million. I went up to a place in Canada about 10 years ago that was a solar cell manufacturing thing. The Canadian government had plowed $250 million into this place. Huge manufacturing facility for solar cells, and they tanked. If you really look at the economics of solar cells, you can't quite get there by the old make a huge ingot, doesn't have to be a single crystal, but even a great large grain polycrystal, and then cutting it with diamond saws. It's just too much saw cutting, and that's why Professor Sachs started this company with edge-defined film growth, so you'd grow it as a thin sheet, and you don't have to saw cut it. Yep.
Did you show the string ribbon is actually not as economical?
Pardon me? I didn't.
You show the string ribbon isn't as economical either, because it's so slow.
Yeah, well, one of the problems with this edge-defined film growth, I mean, I was out there at that lab, and you know, they have nice machines and it works, but it's really slow. I mean, when you're pulling something that thin and that light, you don't make very many pounds per hour. And so this is where you get to Sprague's law. You know, whenever you first hear about a new material, those are the best properties you'll ever have. And Williams' corollary, whenever you first hear about the cost of a new material, that's the lowest cost it will ever have. And a lot of times people don't even run the numbers to say, how fast can I grow it? How fast can I make it? And if you take my casting lecture, I prove why nanotechnology will never be a structural material. Nanotechnology has to be formed from the vapor phase, and the kinetic theory of gases says the fastest you can go is about 1 millimeter an hour. Well, how many Golden Gate bridges or Oakland Bay bridges are you going to build at a millimeter an hour growth rate? You know, with $1 million equipment. What I wanted to say about this New Hampshire company, they're making, I mean, very nice facilities. They're making a lot of money. They're going to make it for a very short period of time. They're going to sell the technology to make these large grain sapphire, large grain silicon to the Chinese. The Chinese are then going to put their low-cost labor into it with their government subsidies and everything else. And they're going to wipe out all the other people who are trying to get into business in other countries. Well, these are the externalities, okay? And the political realities of trying to make advanced materials in an area that, well, it's politically it's good because it's environmentally clean, but frankly, you have to have government subsidies right now to be able to justify putting solar cells on your house, okay? You know, that we passed a law in Massachusetts that 10% of our energy or electricity will come from renewable energy. It's a wonderful thing. It encourages things, and they're building this huge wind farm off Nantucket, and the people in Nantucket are very unhappy, or Martha's Vineyard or wherever. They're very unhappy because they're going to have these great big propellers outside their, wherever they look, they're going to see propellers going around very slowly. But it will be renewable energy, and we all get to pay about 25 cents per kilowatt hour for the privilege. Now, you don't know what you're paying because you're not homeowners, most of you. I'm paying 15 cents a kilowatt hour. But, you know, if only 10% of my cost comes in at 25 cents a kilowatt hour, I only see about another 2.5 cents. Or actually, I don't even see that. I see another penny. It's a 6 or 7% increase on my electric bill. But a 6 or 7% increase on everyone's electric bill in New England is billions of dollars. Okay, so they passed a law that basically says we will have renewable energy, at least 10%, and we will. But you're going to end up paying for it. But if it's just a hidden tax, okay? But it's a hidden tax that's good for the public good. We don't make CO2 and things like that, okay? So anyway, before I get to that, maybe I'll hop right. And by the way, I pointed out I'm going to be here tomorrow. I'll be here on Monday, and then Dr. Belmar will be here most of next week. My trip to California got canceled or postponed, and so I will be gone to Houston and maybe some other places next week. So anyway, I decided a couple of days ago, so for 30-some years, maybe 35 years, I've been getting this magazine, which is the kind of monthly magazine of the American Society for Metals. They changed their name to ASM International back in the 90s when everyone thought metals were dying and they didn't want to be part of a dying industry, so they're advanced materials and processes. And so I'm looking at this kind of the other day, and I thought there's a lot of things in here that you've learned enough about material selection that we can explain. And this is the type of media reporting that you get from supposedly professional societies. But basically, they have in the beginning of the thing, then I put some yellow highlights on, they'll have little quick news articles about some new development. And basically, a company may have some person or some professor may decide he wants to promote his research. So he'll write up a little spiel for them and send them a picture, and they're just looking for copy to fill up their magazine, right? And so they'll report it without any critique. This has all the scientific rigor of the internet, okay? But it's been around longer than the internet. So here's a skyscraper that was designed in Sweden, and it's going to be, they say, wouldn't this be some size skyscraper? But they're going back to a 34-story wooden building, residential building. I thought, wait a second. And the 34 stories caught my eye because I think I already told you the reason New York City went from 10-story buildings to skyscrapers was because Bethlehem Steel learned how to roll I-beams around 1900. Before that, without Otis elevator and without steel for the core structure, brick buildings, wooden buildings couldn't be more than 10 feet tall, and no one wanted to walk more than 10 stories up and down from their office to get to their office. So 34 stories, I thought, whew, out of wood, you're really pushing the limits of whether the wood will collapse and split under its own weight, because wood has very anisotropic properties, right? So you read a little further, which will be built over a wooden construction with a concrete core. Ah, now I know where they're getting the strength. Concrete has tremendous strength in compression, not so great in tension, but it's got very good strength in compression. And so they're going to build a wooden and concrete structure. Now, how can you even build a concrete structure 34 stories tall? Because 10% of it will be steel reinforcement inside the concrete. Okay, so don't tell anybody about that. Okay, but read on. Wood production has no waste products. Well, to a certain extent, that's true. We generate lots of sawdust and all the wood chips that come out of the bark and things like that. But you can sprinkle those on your lawn, or mulch for your garden, and you can burn some of that in wood pellets and things like that. So, yeah, we don't have a lot of waste wood products. I'll go along with that. Bind CO2. Wood binds CO2 because trees breathe carbon dioxide. We breathe oxygen and exhale carbon dioxide. Trees breathe carbon dioxide and exhale oxygen. It's the opposite. Okay, sort of a symbiotic relationship between mammals and trees, plants. Okay. Anyway, but bind CO2. It only does that when it's living, okay? And once you cut it down, it's no longer binding that CO2, okay? But nonetheless, you got to have forests to grow the wood, okay? But let's think not just about the wood in this building. Let's think about the other things like the concrete. Where does concrete come from? Limestone. And limestone has a chemical formula of calcium, magnesium, but calcium carbonate. And what you do is you heat that up and you make burned lime, calcium oxide, plus CO2. So, is this a CO2-free building? Not exactly, okay, because there's probably more weight of concrete in this than there is of wood, given the fact that the concrete's 3.5 times as dense by weight. So I'm cheating there because I use the word weight rather than volume. If you want to do it on a volume basis, maybe it's equal, I don't know. But there's just simple little words, like am I comparing on weight or am I comparing on volume? If the two things have very different density, you have to say, should you be comparing on a volume basis for a structural material or a weight basis? Might make more sense to be a volume basis. We usually talk about weight. And it turns out wood is very strong compared to its density, its lightness, okay, density. This is the strength to weight ratio, the specific strength, yield strength divided by density. And people can do things like that and use those phrases all the time. And they do that for the unaware. And you should not be the unaware. I mean, you're MIT grads, or soon will be, or whatever. I gave a talk. I was sitting actually in the old Chipman room. This was probably 20, maybe 25 years ago. And a young professor, Gary Wennick, was in polymer science, and this was at a time people had just discovered things like polyacetylene, which were electrically conductive polymers. And he was up there giving a talk, I don't know, to the visiting committee or somebody about his research, and he said, these conductive polymers have a specific electrical conductivity. That means the electrical conductivity, which is the inverse of resistance, divided by the density, that is better than copper. And I thought, wow, that's pretty good, because copper is the best we got. And that was copper is a huge industry. And at first I thought, wow, is this going to wipe out the copper industry? And he says, and so because of this specific strength, we will be using in the future, this was like 1985 or something, he might have been saying this, 1990, We will be using electrically conductive polymers in rotating machinery like electric motors or big generators or whatever. And that all sort of made sense. You know, it's spinning, you want lightweight, and if it's got a better specific electrical conductivity. And then the next morning, while I was shaving, I almost cut myself. I realized, wait a second. That is not the criteria for selection of the material that you're winding the motors and things out of. Because today, that time, 1987 or whenever this was, we were winding motors out of aluminum. And aluminum has a better specific electrical conductivity than copper. It's 40% lower electrical conductivity, but it's got 1/3 the electrical, the density. And so aluminum has twice the specific electrical conductivity of copper. But we were making motors out of aluminum, but we were not making great big generators. The bigger the thing, the more you want lightweight, right? We were still making them out of copper. And I thought, well, if specific electrical conductivity is the parameter of interest in the design of this material, why am I still using copper in these $1 million machines? I mean, I obviously could afford, in fact, aluminum's cheaper than copper. I could use it, okay? So you have to be careful. People will sell you on a specific material property, not specific in terms of divided by density all the time, but they will sell you on a material property that is not the property of interest. It's the one they want to sell, okay? If they don't really have, so turns out we do have electrically conductive polymers now, and we use them for touch screens and things like that. But they haven't replaced copper in big generators, in a lot of motors. I figured that out the next morning after he gave his talk, and back in the 1980s. But I was still reading that all through the 1990s of how this electrically conductive polymers was going to take over the copper industry in the world. Don't think so, folks. Because I realized out of common sense, remember I told you, you actually already know the answer, okay? You may not have thought about it, and I didn't think about it when I first heard them. It was when I was shaving the next morning that I realized that aluminum was already a better specific electrical conductivity than copper, and we hadn't switched over to aluminum. It would have been an easy thing to switch over to aluminum, but we hadn't. So obviously there must have been something more in the design that I didn't know about. And it turns out we are still not using these conductive polymers to anywhere near the extent that all the researchers were touting them. Now, I've been through about a dozen of these tremendous revolutions. One of the first ones was structural ceramics, okay, in the early 1980s. Ceramics had excellent high temperature strength. They were supposedly corrosion resistant. They're not, but they were supposedly corrosion resistant. Certainly they're corrosion resistant to a lot of things that metals corrode in, but ceramics don't. But ceramics will corrode in other things. And the world was spending billions of dollars in research for what they called fine ceramics. So now, 30 years later, what do we make out of fine ceramics? They were going to make automobile engines. They were going to make turbine engines for aircraft. And what do we make out of? I got some knives at home. Excellent at slicing onions, okay, because they're sharp, okay? They don't crush the cells and release all those things that make you cry. They actually cut through the cells and don't release as much of the juice. Yeah. What? Yeah, they do. I mean, we've always made, in fact, in the mid-'80s, I used to give this talk and say, we're not going to have structural ceramics because they don't have fracture toughness. Look at that piece of silicon, the little flat piece that's got the chips on it. Look at my knives in my kitchen. They don't have tips on them. They got chips on them. You know, they're great. They retain their sharpness as long as they don't chip off and turn into something blunt, okay? And they only cost $100 a piece for a knife that you can go and buy one for $5 or $10 out of steel. But I like them, and My daughter-in-law really liked them. She used to chip them all the time. In any case, it never became the huge market. Then there was the conductive polymers. Then there was high temperature superconductivity. I told you, some of you offline, the story of I was department heads, mid-90s, and I had to give a talk over in Little Kresge to a bunch of people from industry. And someone asked me a question about the new high temperature superconductors that had just been discovered like 5 or 6 years before. And I said, they're fantastic functional materials. We're going to use them for detecting magnetic fields or optical sensors or things like that. But all this stuff you hear about high field magnets, we won't see those in our lifetimes or our grandchildren's lifetimes. Got back to my office, it's about 5 or 6 o'clock in the evening, get a phone call from a faculty member in the department, and he had heard already what I had said half an hour before, and he just lit into me about, you don't know anything about superconductivity. I said, Mike, I did my doctoral thesis in superconductivity. I think I know something about it. Well, he just blessed me out, and I finally said, quit acting like an 8-year-old. I have a right to my opinion. Well, he took me to the dean. And the 3 of us sat in the dean's office, and the dean says to me, Mike says you called him an 8-year-old. I said, well, I'll quit calling him an 8-year-old when he quits talking like an 8-year-old. Okay, the dean's kind of, he thought he was going to smooth this over, but I'm not. Don't try to smooth it over with me, okay? Anyway, but this faculty member, because he had research in high temperature superconductors, he told me we would be riding on levitated trains within 5 years. Well, it's now about 14 years, it's about 17 years later now, and I still, if I ever go over to the cancer center and see this guy again, I'm going to ask him where the levitated trains are, okay, because I haven't been able to get on one yet. There are other problems, and you actually have to know some details about something to understand it. You can't get your knowledge off the front page of the Wall Street Journal. I mean, I go over and teach a class over at Sloan, and these guys and gals, okay, I got in trouble once for saying that, men and women, okay, they're reading the Wall Street Journal before class in the morning. And I used to tell them, by the time you read it in the Wall Street Journal, it's not news, okay? Everybody else is reading. You need to kind of get there a little earlier, okay, before everyone else reads it. And just because you read it there doesn't mean it's true. One of the things right now, they've run some articles on additive manufacturing in the Wall Street Journal. So every CEO in America thinks, why are we doing machining and cutting things apart? We should be adding metal, and we should be doing 3D printing. And you read all this stuff about 3D printing. Well, again, 3D printing, let's talk about rates of manufacturing. And it's great. I mean, Tiffany's, when they're making the Super Bowl rings, they make plastic molds in a 3D printer with shooting wax, making wax molds. And then they do lost wax casting to make the thing, because they're only going to make 150 rings. Say, why do you need 150 rings for a team of 53? Well, there's all the coaches, and there's the lawyers that work for the owner, and there's the owner, and the owner gives rings to his friends. So they actually probably do make 100 to 150, okay? And they're very valuable rings, okay? And you can get even more for them if you can find, unless OJ wants to take it back. No, that wasn't a Super Bowl ring, was it? But anyway, it's very dangerous to buy some of this stuff, right? In any case, so when you read these things about wooden buildings, kind of read between the lines. And to me, this is sort of like running. I don't need to read the comics. I can read the AMP latest and greatest science. There's some more here. Siemens Metal Technologies is going to sell a $140 million plant to some Chinese to build a complete cold rolling complex. So the Chinese don't have the latest and greatest process controls for rolling steel. So what do? They buy it from us. Back in the 1990s, or actually in the 1980s, I showed you the big productivity increase in steel. It was like a 2-fold increase in productivity from 1980 to 1990. and there was the change to continuous casting, which went from, in the 1970s, went from 65% yield to 97% yield. All of a sudden, the world had 30% more steelmaking capacity than they needed, and the price of steel dropped. And a lot of those companies that first went out of business, they'd sell their old equipment to try to make a little money to Brazil or Argentina or Saudi Arabia or something. And then after about 5 years, they realized their other mills couldn't compete because they were now competing with their own equipment down that they had just shipped and sold for 10 cents on the dollar to some other country. And so by the late 90s, if they went out of business, they would sell their mill for scrap rather than sell it to someone else who's going to re-enter the market using their equipment against them. This has happened many times. I ran into this in shoe manufacturing back when I was an assistant professor. United States, New England used to be the center of shoe manufacturing. The Gordon McKay School of Engineering at Harvard, or Applied Sciences. Gordon McKay was a wealthy shoe merchant in Boston. He gave $10 million to Harvard in the early 1900s. And now the Gordon McKay's name is all over their School of Applied Sciences, professorships and everything, out of shoe manufacturing. Well, I had to go up here to the North Shore. There was a guy going into these old mills, taking the old shoe machines from the 1930s and rebuilding them and selling them to third world countries. And they would make footwear, which would come back to the United States as low-cost shoes. Well, so we were selling, just like whether it's the New Hampshire company selling the technology to make silicon solar cells, or sapphire substrates, or steel companies selling the technology, the old equipment, or selling the new equipment technology. There is this thing about, you know, the more technologically advanced countries are going to sell their old equipment or their new equipment to the less technologically advanced, and then they're going to see those people come in and beat their socks off in the marketplace, and then they complain about it. Well, okay, I mean, you better keep developing technology and keep ahead of the game. So that's some of that. So I read this, and it talks about plastics in oil sumps drive down vehicle weight, blah, blah, blah. Okay, well, what happened here? This is another one of these little articles. If you have some questions, you can stop me, okay? So they're using polyamide 6. Anybody know what polyamide 6 is? We have a more common name for it. It's called nylon, okay? Rather than calling it nylon in this article, they say polyamide 6, as if it's a new material. Well, this was new in 1935, okay? 35% glass reinforced. We've been doing that for about 50 years. Heat stabilized. Okay, I don't know exactly what they mean by that. Maybe they remove some of the stresses. But anyway, 60% lighter. Okay, it's lighter. Now, compared to the old aluminum or steel oil pan. Now, they had to do curb impact test. I don't know how you hit your oil pan against the curb unless you're jumping the curb, but no, never mind. Stone impact test. Well, you could get stones kick up, and it's not as ductile. Actually, it could be more ductile. Anyway, and an engine drop test. Engine drop test. I don't know what those things mean. But does anybody notice what struck me looking at the picture of the screws? Look how closely spaced those screws are around that oil pan. Anyone ever looked underneath the car on a steel or aluminum oil pan? Does it have screws that close? No. Why? You're a material scientist now. This is not as stiff. The steel is stiffer, and the modulus, the stiffness of the material, determines how closely you have to put the bolts in order to get the seal. Okay, if it's a rubber in between, the thing's just gonna, the seal's just gonna bow, and you're gonna lose your seal. So I just doubled the cost of my bolts. I don't know if they included that, and I also have to install and tighten all those bolts. Okay. And if anyone ever has to take the oil pan off, they got to loosen all those bolts. So there are trade-offs. So I'm not saying this isn't an interesting development. And you can see they made a honeycomb structure so they could get the strength that they think they need and the impact resistance and stuff. And it may be a great application, but the nylon is going to go for $4 a pound, $6 a pound. The steel or aluminum is going to go for, the aluminum go for $2 a pound. The steel will go for $1 a pound. This is lighter, and so you don't need as many pounds. And if we're talking volume, which is the right weight, maybe volume, this is a lot thicker. In any case, there are some interesting material selection issues here. Now, they also announced in this magazine that Alcoa in the United Kingdom is putting in a 3rd generation aluminum lithium alloys. We haven't gotten to aluminum alloys, talk about specific alloys, but they can put up to 10% lithium in aluminum. And it's very interesting because ordinarily alloying doesn't change the modulus of the material, the stiffness of the material very much. But 10% lithium, that's by weight, so it's actually a very large atomic percentage when you're dealing with something as light as lithium, increases the modulus from about 10 million psi to 11 or 12 million, depending on how much lithium is in there. And a 10 or 20% increase in modulus is great, but it's also so light that the density is less. And so the specific modulus is like 30% greater. And it turns out, when you're designing an aircraft, specific modulus is the metric of what you want to design this thing for lightweight structures, okay? So about, well, actually in the mid-70s, they first came up with this, and it was a huge research project. It took them about 20 years to resolve some of the corrosion resistance problems. And it says better stiffness is it is better stiffness, but it's even better specific stiffness. Damage tolerance. I've used a different term for damage tolerance. Fracture toughness. Okay? Same thing. We're just using different words for the same thing. So one of the things you need to learn is what all this vocabulary is. Certainly, I mean, they say stiffness. Well, what's that in a material? To a material scientist, stiffness is modulus. What's damage tolerance to a mechanical engineer or materials engineer? That's fracture toughness. What's corrosion resistance? That's corrosion resistance. But people use different terms and to impress people. Down here, contract to produce composite aft fan cases. This is for the Rolls-Royce engine that is going to power the A350. In the fan case they're talking about is, I think it's this one right back here, the aft fan. This whole thing is the fan, part of the engine, and the aft is in the back. So I think they're talking about this thing is going to be a composite material. I'm going to spend some time talking about composites and their advantages and disadvantages. But in fact, composites are inherently going to be more expensive. But if I'm in the aerospace industry at $200 a pound, or even more if it's off the engine weight, which saves weight on the rest of the structure, I can afford to use something that might cost me $1,000 a pound. Okay? So this is potentially a good application for composites, and they just gave the Rolls-Royce just gave the contract to ATK, Alliant. It's Alliant Technology. I can't remember what the K stands for. But they're in Magna, Utah. And what were they famous for? Anybody know what Alliant built that blew up? Space Shuttle Challenger, the seals. That was all Alliant Technology. They designed the seals for the Challenger that caused the Challenger to blow up. And it was an engineer, Boss Jolie at Alliant, said, it's too cold, don't fly it. Okay, but they were going to fly the Challenger. Anyone remember the reason why they were going to fly the Challenger? Yeah.
They said that they performed missions before.
Well, actually, they said that, but that wasn't really true. The real reason, the real externality, because Krista McAuliffe, which is a school teacher from New Hampshire, she was going to talk to Reagan, President Reagan, during his State of the Union address from space that night. So none of the top managers wanted to cancel this for some stupid technical reason, because they had a big political windfall where the school teacher from New Hampshire, the first school teacher in space, was going to talk to the President of the United States by satellite phone during his State of the Union address that night. if she wasn't up in space, it was, here I am from the Holiday Inn in in Cape Kennedy, okay, rather than here I am from 120 miles above. Anyway, so there was a political reality there, and the engineer who says it's too cold, the O-rings are too stiff because they're so cold, it's not going to work. And they had previous history of the O-ring damage. They had double O-rings for some redundancy, and they had almost blown one of these things before when the outside temperature was like 40 degrees, and now it was 28 degrees. So yes, they said, oh well, we've flown cold missions before. Yeah, but never this cold. Okay, but that's just someone trying to gloss it over. Yes, you had a question?
I just had a question back about the aircraft engine. Are they able to make composites that fail a little bit more? Because obviously those engines, they do that like C4 tests, right?
Yeah.
Like, I guess if you have an aluminum covering, right, it's a little bit more a ductile failure or plastic
yeah,
beforehand.
but frankly, if you get something that hits it hard enough that aluminum's going to dent, once it dents, it's not going to operate properly anyway.
Right.
The fans are not going to, the blades are going to go flying off, because once you get oval.
Yeah.
So no, the composite is not as damage tolerant. Okay. Have they designed as much damage tolerance as they need into the composite? You bet they have. They're concerned about that. It's a $5 million engine at that point, okay? And it's a $10 million nacelle, and it's a $200 million aircraft. And it's a $1 billion lawsuit for the people who die. So, yeah, there are financial consequences of all of this. And believe me, the people in the aerospace industry are sensitive to this. They're good engineers. They know what they're doing. So I read an article about, the aft fan case. This is not done for political reasons. In my experience, I've never seen anything in the aviation industry where people were doing it for purely political reasons. They're doing it for economic or safety reasons. Okay. Or just, you couldn't do it otherwise. I actually have a picture in here of the V-22 Osprey. Just happen to have a picture of the Osprey, which is what the Marines call it, the tilt rotor. What do they call it? Actually, maybe they call it the Osprey. But anyway, this is the tilt rotor helicopter. So the two rotors on either end will come down, and they used one of these to get Osama bin Laden. But basically, you have to understand, well, does anyone know why a regular helicopter is limited to about a 200 mile an hour forward speed? It's the blade speed, it's the tip blade speed, and it's the advancing tip blade speed. When that goes supersonic, you run into all kinds of stability problems. If you go down to Langley, Virginia, to the materials lab, right outside they have a helicopter that they once put some rocket motors behind, and they actually flew it with the rocket motors pushing it forward to like 240 miles an hour. And so the blade tips had gone supersonic on the advancing blade tip. Okay, so maybe it's only 200 miles an hour going forward for the fuselage, but the advancing blade tip is going a lot faster than that. And once it gets to 600 miles an hour or 650, whatever Mach 1 is, you get all types of instabilities, and that can cause the blades to break up, and that's not a good day for the pilot or any of the passengers. Okay, but they've done it because NASA wanted to do it, and I'm sure the guy had, parachute to eject and everything, because they wanted to study the instability to see if they could get around it. But basically, you can't really, the instabilities are not something you get around. So Bell and Boeing developed the tilt rotor so that you can operate in a helicopter mode with the rotors up, or you can it's a tilt rotor, you can tilt the rotors forward so you have a propeller going around like a regular aircraft. These guys can go at about 300, 350 miles an hour. They also don't make as much noise as a helicopter blade running this way as opposed to a propeller running this way. And so they can't hear you coming. And you're coming at 350 miles an hour, not 200 miles an hour. The Marines consider this a significant advantage. And they did use one in the getting Osama bin Laden, although most of them were Sikorsky Blackhawks. I'll tell you some more about Blackhawks later. But anyway, where are we now? I knew I'd finish. I couldn't finish all this because there's just too much good stuff in here. Does anyone know why the aircraft, the engines look like this? With the big, instead of the old engines, back when I was your age, you look at the side of a jet and it had this hot dog shaped thing. It didn't have this great big fan up front. Anyone know why in the 1990s we switched from just pure jet engines where you just take the gas in, combust it, and shoot it out the back, to switch to the turbofan, which is different than a turboprop. A turbofan is a jet engine with a great big propeller on front. This is just a great big propeller. Does anyone know what the basic physics of why they went from the old hot dog sausage shape to this great big thing? In fact, they would like to get rid of this shroud. General Electric had a design that it was just a propeller up front with no shroud around it. Yes?
Just to get more oxygen into the engine so you can burn hotter and faster.
It has to do with the gas flow, not specifically the oxygen. They already are compressing in the compressors. They've gotten up to like 30 atmospheres. And at 30 atmospheres, at those temperatures, you can't compress it a lot more. I mean, they have gone to higher than that, but you've got about all the compression you can get efficiently. Yes?
You have a single shaft, and you need to have a higher pressure region and lower pressure region. Since you're running the same two compressors off the same shaft, you can't.
You're getting there, okay? They actually do have to have two shafts here because there's one shaft that's going to spin this fan at a different speed than the compressor inside. So it is a double shafted engine. It's a lot more complex. Price of engines went from $2 million to $5 million, okay? But it all gets back to there's something called kinetic energy, 1/2 mv squared, and there's something called momentum, mass times velocity. If we're talking about the gas, okay, there's a certain mass of gas. One of them, which is what's coming out the back of the engine and goes through the compressor and everything and generates all this extra energy from combustion, that's the 1/2 mv squared thrust, okay? But you can get a lot more thrust if you can actually pass gas not at near sonic velocities out the back, but at less than sonic velocities over a much bigger volume. That's the fan up front. So this, if you want to think about it in very simplistic terms, this is the momentum. The fan is the momentum pushing air to give you thrust, and the kinetic energy is what's coming out the tailpipe to give you the kinetic energy thrust. These are hot gases. These are cold gases. But you get more thrust out of these cold gases now than you ever got out of those other gases. Now, and this is a divergence between military engines and commercial engines. Before that, back through the 1970s, early 80s, military engines would push the technology, and then the civilians would come along and say, oh, great, we'll just take that technology improvement in efficiency and put it on our aircraft, our civilian aircraft. Starting in the 80s, when General Electric and Rolls-Royce and everybody else started looking at this basic concept of you really want to move the greatest mass of gas. You want this M to be huge, and that's what goes through the fan. The M that goes through the engine is a lot smaller M. Before, the two M's were the same. When they decoupled and had a fan, this is sort of the engine, and this is the fan, M. You have two different masses, and you have a much bigger mass, lower velocity, but a huge mass gives me more thrust than small mass and huge velocity. Okay, and they worked, the aeronautical engineers worked all this out, and all of a sudden, the military engine development, which wants to go supersonic, okay? You can't go supersonic with a fan, okay? Just like with the helicopters. Those fan blades start wobbling and they break off, okay? But the military wants to go supersonic for strategic reasons, tactical reasons, and so they don't have big fan engines except on their transports, but on their fighter jets, it's a completely different engine now. But until the 1980s, they were basically the same. It's sort of dual use technology. Well, now it's not dual use. It's a problem economically. So anyway, I've done enough of that. I'll go back tomorrow. I'll do some steel processing and show you some other things that happened in the last 25 years that have taken steel on about a tenfold reduction in improvement in productivity. And then we'll do aluminum, and then we're going to get into each specific metal and go that way. Okay?